Okay, welcome back. So let's continue to the second section for today's lecture. Okay, we are still discussing our tutorial. Okay, so there's one more question. Tutorial 4, question 6. Right. I will just focus on questions 6B only. Okay, because question 6A can actually solve by using the similar methods. All right. So so let's look at the solution for question 6B. Okay. So again, omega is the unique interval 0 to 1. And as usual, we take the sigma field to be the Borel sigma field. And as usual, we take P to be the uniform Levet measure on omega. Okay, so we define this random variable xn to be n square of this. So we're going to find E of lim sub xn and lim sub E of xn. Okay, the reason is we want to compare with this reverse factor lemma in question 5. So we're going to look at it later. Let's compute this two expectation value first. Okay, right. Before we start doing this, okay, maybe this is the thing that we need to recall some properties. Maybe before that, don't just look at some properties. For limiter. So again, first of all, limit infimum of xk always less or equal to limit supremum of xn. Okay, so this is always less than this. So B. When these two are equal, okay, when lim in of xn equals to lim sub of xn, so then we just simply define. We just simply define limit of xn to be this. So since they're equal, so that means they are equal. So, right. So that is how we define the limit of xn. So we just compute lim sub xn and lim in xn. So when we see the value are the same, so we say this is the limit of xn. Okay. Okay, now we can, having this picture idea in mind, so we can look at our questions, solution question 6B. Yeah? Okay, so in this example, so we said xn is n squared and the indicator functions 0 to 1 over n. Okay, so and omega is 0 to 1. So that means any outcome must be in between this value 0 to 1. So for any omega in between 0 to 1, and we know this, we know that for any positive number omega, we can always construct, find an integer m with omega is greater than 1 over m. Okay, when omega is greater than 1 over m, so meaning that it does not belongs to this. It does not belongs to this interval. So then x of n omega will be equals to 0. So then we can have this. So xm omega will be 0, and also x of n omega will be 0 for all m larger or equals to n. So because of this is equal to 0, then we can have this, hence limit of xn will be equal to 0. Okay, based on our assumption here, so when limit exists, so then it always equals to the lim sup of xn over here. So then from this, then we can see this already. Okay, then we have this, hence this number 1, e of limit supremum of xn, so which is actually equals to limit of the e of lim fx xn, so that will be equals to 0. So this is part 1. Okay, for part 2, we wish to compute limit supreme of e of xn. So for part 2, so e of xn, so according to the definitions, so this will be xn will be n square 1 of 0. This. So then we can have this is a 0 and then p of this 0 to n. So that is equal to n square. So 1 over n minus 0. So that's why this is equals to n. So then it's very clear. So limit supremum of e of xn will be, we are taking limit, so this will be equals to infinity. Okay, so this is an example whereby limit supremum of exn is not less than e of limit supremum of xn. So this is one example for it. And because of the right hand side 0, the left hand side is equals to infinity. Okay. Okay, so next will be this. We go back to our questions. So the question asks this. The question asks this. Explain why xn does not satisfy the reverse factor lemma in question 5. Okay, so that means we come back to here. That is actually this. This is not less or equals to this. Then we just look at the statement for reverse factor lemma question 5. Okay, this is the statement. Okay, reverse factor lemma. So in this reverse factor lemma, so we need two hypotheses. Okay, so number 1, xk must be less than one random variable z, and we also need another hypothesis. E of z will be less than infinity. If this is true and this is true, then we can have these inequalities over here. Okay, so if these two conditions fail, then we might not able to obtain this inequality. Yeah, so that is the reasons over here. Okay, so why is that so? So the reason is here. You can look at our e of xn, so which is always equals to n. Yeah, so we look at this. So because of E of x n is equals to n. Okay, and so we cannot find a random variable z with finite mean and greater than xn. Okay, we cannot find it. So because of E of xn will be this, right? So if this one less than this, then this will be always infinity. So we can see this, for example, for otherwise. So if xn less or equals to this, or n, then we must have E of xn must be less or equals to E of z. In other words, n will be less or equals to E of z. So that means we must have this must be greater or equals to infinity. So then, so hence we can say that hence cannot be equals to infinity. So that means this one cannot be whole. Okay, so that's the reason why we cannot apply the reverse factorial lemmas over here. The reason is we cannot, because we cannot find a random variable n with both this and this. Right, so I think that's it for our tutorial 4. Okay. Yeah, so good. Before we continue to our chapter 5, so do you have any further question on this tutorial 4? So I would suppose no further questions, right? Okay, great. Let's carry on to another sections. Yeah. Yeah, I think I better use a new page. Okay, so this is the last part for our chapter 5. Yeah. So part 3 for chapter 5. So that is only one section. So sections 5.5. So we're going to discuss both versions of law of large number. Okay, so in So this is the thing that we want to discuss. Okay, let's look at our setting here. So the setting will be that. So we consider a sequence of random variables. So x1, x2, x3, and so on. Yeah, we consider a sequence of random variable. Okay, maybe this is okay. First, we just simply write this. Assume e of xi will be equals to 0. So again, this is just to simplify our formula. So not necessarily this. Yeah, and b is we can just write this Sn to be x1 plus x2 up to xn. So if we want to use a summation notation, so that will be we summating I from 1 to n for xi. So having this, then we have these questions. So under what conditions, then I'm going to have Sn over n will converge to 0. So we want to identify what condition that we want to, what hypothesis that we need to satisfy in order to get this situation. Xn over n will converge to 0. Okay. So again, so in the beginning of chapter 5, we have discussed several types of the convergence, right? So here we consider 2 different types of the convergence. Okay. So here, we consider 2 types. Okay. That is, first of all, xn over n converge to 0 almost surely. And the second one, Sn over n converge to it in probability. And if you refer back to the summary in section 5 regarding to all those the convergence. Okay, maybe I copy this. Okay, so this is you refer to supplement. So this is from the chapter 5, supplement A. Okay, so we have a relationship among these 5 modes of convergence. So converge in quadratic means always imply convergence in L1. Convergence L1 to implies convergence P. Convergence P implies convergence D, and almost surely convergence always imply in property. So if you look at here, just look at this and this. Okay, so which means this always implies this. Okay, so this one always implies this. So that's why this is stronger than this. So that's the reason why we call this one as the strong law of large number, and this one implies, so this is weaker than this, so that's why this is the weak law of large number. Okay, so both 2 versions we call it law of large number, but it will be in a different kind of the convergence. Okay, so the first one is almost surely, and since almost surely always implies convergence in probability, so that's why this version is the stronger version. Yeah, so that's why we call it, this is a strong law of large number. So this is the weak law of large number. Okay, that's the thing. Okay, come back to here. So here is our study. Okay, not our study. Actually, the main study. One of the main study in probability theory. That is, for what hypothesis that we can get this conclusion, Sn over n converge to 0. Okay, so of course now we have quite advanced study in these topics already. So there are several different kind of hypothesis over here. However, in here we only consider one hypothesis. Okay, so here we only study one of the hypothesis. That is, we look at the IID, independence and with identical distributions. Okay, so now this is when all these random variables are independent, are having the same distribution, then we can have this law of large numbers here. Right? Okay, so let's look at the first one that we consider here. Okay. Let's begin with the first one. I think I better write now. Okay, so the first one will be this theorem 5.5.1. Okay. Okay, so we have this hypothesis. Okay, suppose x1, x2, or maybe x3 and so on are independent and IID independence and having the same distributions. Okay, and secondly, we assume E of xi is equals to 0. Okay. And C, and if we assume sigma square, that is the variance of each of xi is always positive and finite. Okay, if we have this, and then we have these conclusions. Sn over n converge to 0 in probability. Okay, so this is the first version that we consider. So this is so-called the Chebyshev weak law of large number. Okay, so here we need 3 hypotheses. Actually, 2 is enough already. The second one is just to make our formula looks nicer. Yeah, basically this is independence and having the same distributions. And the second one will be the sigma will be in between 0 to infinity. Then we're going to have this hypothesis. Okay, before we look at the proof for this, right? So maybe we can see if we make a change with this hypothesis, what can we have? So just look at this. Okay, remark 5.5.1. So if we replace this, if we just change this hypothesis, so let's say instead of 0, so let's say we say this is Okay, so this mu could be 0 or might not be 0. So if we replace this with mu, then what we need to do is we just need to switch our formula to this. Okay. So that's why, as I said, the second hypothesis here, 0 mean is not really important. So we put in the second hypothesis here. It's just we want to make our formula looks nicer or easier. Okay. Yeah. Please take notes of this. Okay. So when we replace 0 with mean, so we just replace this to be the mean over here. Okay. Okay, so then we can look at the proof for these theorems. So actually it's not that difficult. So what we can do is we can just apply the macro inequality for it. Okay, before we prove this, I think maybe before we prove it, we need to recall this definitions. Okay. Okay, just record it. Let's say we have a random variable y. Okay, since we're using x, I put another one. So we said that yn converge to y in probability, provided that limits of p yn minus y greater than infinity, epsilon is 0 for any positive epsilon. So this is actually the definitions for convergence in probability. So that's why this is something that we need to verify over here. Yeah. So then we can look at a proof for these theorems. So if we using this, we can just replace this with 0. So that means what we want to do is we want to show this limit n to infinity for Sn over n minus 0 greater than epsilon is equal to 0. Okay, of course, the 0 here depends on whether we want to put the mean to be 0. Okay, we want to show this. Okay, now we know our objective is to verify this limit is equal to 0. Yeah. Okay, so then we begin it. So we can take any positive number epsilon. Yeah. So when epsilon is a positive number, then as usual, we can look at it. We just look at this region. Okay, epsilon greater than this or greater or equal, doesn't matter. So in this region, Sn over n is greater than epsilon. So if we restrict to this region, Sn over n is greater than epsilon. So which means, so if we multiply epsilon, so this will be always less than or equals to this Sn over n. So this is always true, okay? And we can actually do some further things. We can square both sides. So we also have the same inequality. And also, this indicator functions is always less than 1. So this is always less than 1. So therefore, then we can have this. Yeah, so this is a very common technique. So we actually use it quite frequent over here. Alternately, you guys may use the Markov inequality to do it. So if we look at these two terms, so just this part and this part, then we actually got this inequality, that is epsilon square less or equals to this. So then we can now take E both sides. So then this will be less than this. So for the left hand side, so I think it should be theorem 4.1.3. So using theorem 4.1.3, so we can directly get this. So the left hand side will be equals to epsilon square P of this. Just let you know, this one to here we are using theorem 4.1.3. Okay. So this step 2, this is straightforward. So this is also remain less than. So and then this one, E of Sn squared. So then we will get the variance. So it will be a sigma square n over n square. So this will be just sigma square 1 over n. So this is always less than this. Then we can bring it over. Then we can see P of this always less or equals to sigma square over epsilon square 1 over n. Okay. Okay. Now take note that this one is a finite value. Okay. So that's why it's not infinity. Or maybe I just make it clear. So this thing, which is not equals to infinity. Okay. So when this is not infinity, this is a finite value. So then if we take limit both sides, so it won't affect the result. So we can take limit n to infinity. So I think this is 0. So that's 4. This will be equals to 0. Okay, so then you can see, so we have achieved what we want to verify here, right? So like I said, so this is our objective. We want to show this is equals to 0. Okay. And indeed, we are able to verify it. So then that's the end for the proof. So this is the first versions for the weak law of large number. Okay.
Dr. Lu?
Yeah.
Can you remind us again why epsilon squared is lesser than or equal Sn over n squared, the first step?
You mean this line?
Ah, yes, that's that.
Okay. Okay, I think this is, I think it's worthwhile to spend some time to explain it once again. So if you may go back to the recorded lecture. So actually, we have used this quite frequently. Yeah, this technique I think is a very important technique. So maybe spend some time to look at it. So this is actually general, quite general. All right, so maybe we look at it. Just look at it. Just look at in general. Let's say we have alpha here. So this is a random variable y is greater than alpha. Okay. Okay, what's the meaning for, okay, maybe this one first. Okay, let's look at the meaning for it. What's the meaning for it? If we, I think it's understood, right? So here alpha is just a scalar, a constant scalar, okay? And y is a random variable, okay? I think we all agree with this. So what's the meaning for this event? Supposing if we have an outcome, omega belongs to here, what does it mean? So this outcome omega belongs to this event means that y of omega is always larger than this. Okay, y of omega is larger than this. So, okay, this is the case for it. How should I say this? Okay, this is the case over here. And then we look at another one. So look at these indicator functions of this omega. So again, okay, maybe I can say this. So when omega belongs to here, so that means y of omega is greater than alpha, and also the indicator function of this omega. Okay, this is a particular omega. When this omega belongs to here, so this is equals to 1. Okay, this is equals to 1. Okay, this is equals to 1. Okay, now you are, if you combining these two. Okay, if you're combining these two over here, just let's say this is 1 and this is 2. So you're combining 2, 1 and 2. How should I say this? I think maybe I should put 1 over there. That will be a better picture, right? 1 is equals to this. Okay, so then you look at this one multiply this will be less than this multiply this, right? So you are actually you are multiplying 1 and 2. You multiplying 1 and 2, then you're going to have alpha multiplying 1 will be less or equals to y of this omega and 1 of this omega. Okay, this is 1 omega. Yeah, of course, this is not true in general. If we put in this, how should I say it? Okay, maybe I can put it in 1 of this omega must be less than this, right? Y of omega multiplied 1 of this omega. Yeah, I think it's clear. So because of we actually we do not need the second part. We just need this part. So this is always greater than this from equation 1. So usually we do not need 2, right? I think that's the way. I don't know how to explain it because to me this is quite straightforward. Okay, so this is the case. I think maybe this one is better.
Okay, thanks, Doctor.
I hope you get a picture.
Yeah.
I hope I get a picture over here. I think maybe make it clear. Okay, from 1 you can get it. Okay. Okay. Yeah, of course, when omega does not belong to here, both sides equals to 0. Okay, so this is the first case when omega belongs to here. We get this ready. Okay, so maybe you can say this is a case number 1. Okay, let's look at case number 2. When omega does not belong to here. When omega does not belong to here. So this one just simply means that one of this y greater than this omega must be equal to 0. Okay. Yeah. Now when this is 0, right? When this is 0, so which is actually independence of your alpha here. Then we can have this case. Then we are actually getting alpha 1 this omega so this must be equal. The reason is this is 0, this is 0. So 0 equals to 0. Okay, so in this case, we are just focused on this part. Okay, we focus on this part. Both sides equal to 0, so we have equality. This is for the case whereby omega does not belong to this domain. Okay, so when omega belongs to this domain, we focus on this. Y omega greater or equals to alpha. Okay, so combining this, then we have this summary. I hope you can remember this. Okay, because this is a very useful technique. So then alpha 1 of this always less or equals to y. Okay, you just following here. Yeah, if this is y, y. Yeah. Okay, maybe we start off with this. Just start off with this first. Okay, first of all, this is always less than 1. Okay, this is always less than 1. Okay. So, however, for this part, when you multiply, this is alpha. So, you multiply alpha, you multiply here. So, you always get a less than equal. Okay, so maybe this is the way you guys can always remember this. So the first two, we just put in the indicator function, whereas the last part, we can just put it 1 over here. Okay. Right, so I hope you guys can follow this. This is quite useful because you may use it to prove a lot of result there. Yeah. Okay, so that's it for the first theorem. Yeah, maybe just go back to the theorem once again. Okay, so this is my theorems here. I think I better put it over here. Can I make it smaller? Okay, I can. Okay, never mind. So just put it over here. So this is the first theorem, first version of our weak law of large number. So we are putting A, B, C here. Okay, so you can see here we have three hypotheses, A, B, and C here. So in fact, we can remove this. This is not needed. Okay, so which means the conclusion true even we remove this. Okay. The conclusion holds even if we remove this C. Okay, so that is actually another version of our weak law of large number. So that is the second one. Right. We have a next one. So number 2. So this is theorems. 5.5.2. So that is, first of all, again, suppose x1, x2, x3 all independent and having the same distribution, and also B, we assuming that the mean is 0. So as I said, we do not need this. That means we are allowed sigma to be infinity. Even sigma is infinity, we still get the same conclusion. Then we have this. Improbability. Yeah, so that means in future, if you want to apply this weak law of large number, so you don't have to look at the value of the variance. So the variance can be finite or can be infinity, it doesn't really matter. Yeah, so it will not affect our result. So even if the variance is infinity, so that is okay. We still get the same conclusion. So what is crucial is you just need to make sure all these random variables are from the same distributions. Okay, when this is true, then we have this conclusion. Okay. So the proof is actually quite interesting. Proof, right? Okay, so the proof for this is quite interesting. So we are not going to discuss it now. So we will leave it next lecture. Okay. So it will be easier if we use the moment to prove this result. So I'm going to do the proof in chapter 6. Okay, next we look at the examples. Okay. Okay, I think this example has been applied, or this formula has been applied in the undergraduate course quite often. Okay, so now we look at it, how to get this thing. So let's look at these examples. Okay, first of all, we consider independence Bernoulli trial with probability of success P. Okay, so as usual, we just let xi to be 1 if the I outcome is success, 0 when the I outcome is, oh, so I think there's a typo. So this one cannot be both success. So we are interested on success, right? So this one should be fail. Okay. So please make a correction. So I think we all know this is Bernoulli. This xi will follow Bernoulli's distributions. And we assume each star are independent to each other. So that's why they're independent. So then Sn, if we submitting all the xi, so Xn will be the number of successes in entra. And E of xi will equal to P. So this is follow the standard formula. And I think this is clear. So the Week law of large number state that Sn over n converge to P. That means it's mean in, I think this one should be in probability. Again, another typo. So I think it doesn't matter. So this is in probability. Okay. So Sn converge to P in probability. So that is. So this is actually from the definitions, the limit n to infinity, probability Sn minus P less than S1 is equals to 1. Okay. Okay, next, we just state the other version for the strong law of the large number without proof over here, because the proof is quite difficult. Okay, I think I just write it down. Okay, again, suppose we have this x1, x2, x3. All these are IID, yeah? And also we assume E of xi is equals to 0. Again, this one doesn't really important. Okay? Then we can have this. So this is we so-called the strong law of large numbers. Okay, the version of Kolmogorov strong law of large number. So we are not looking at the proof, so the proof is beyond the scope of this course. So I will skip the proof. Okay. So what you need, you just need to apply this theorem without proof. All right. So again, there's only one important hypothesis when this is IID. So again, when this is not 0, you just need to replace 0 with mean. So in general, if you put this one to be mean, so that will be mean. Okay, so that's the only thing that you need to know. Okay, actually the last example shouldn't belongs to here. It's supposed to be belongs to the section 2. Okay, never mind. So since it's here, then we just look at it. Okay. So the last example is supposed to belongs to section 2. I put it in the wrong position. Okay, never mind. Just look at this. Okay. So we have this. Xn is a sequence of random variable with probability. P of x then go plus minus n is this, and this is equals to this. So again, before proceed, so please check, verify P is a probability. Okay. Okay. Show that xn converge to 0 almost surely. So we want to show that xn converge to 0 almost surely. So then we just simply recall to some those criterion for almost surely convergence. Okay. Okay, so again, this is from chapter 5, supplement A. Okay, so this is all the criterion and necessary condition for almost surely convergence. So the first one will be the definition. So xn converge to x almost surely if and only if this is true. So it has several variations, 2, 3, 4. So you can use any one of it. Okay, now we are concerned with number 5. Okay, 5 is a very useful conditions. So we can use it to verify whether this is almost surely or not. However, this is only one direction. That means if this is true, then we can have these conclusions. Okay. So if this is not true, then we cannot have a conclusion. All right. So in this question, we're going to apply this. So apply this to example 5.5.5. Okay, to solve our example 5.5.5. Okay, so just do it one by one. So again, this is the definition for the probability measures. Okay, so we apply the Borel-Cantelli lemma and to prove the almost surely convergent. Okay, so we begin with this. For any positive epsilon, so we have this. P of xn greater than epsilon will be P of xn greater than, okay, so this is quite clear. And this is 1 over epsilon. So the reason is this one is actually here. Okay, so this is if you want to do it, so because of this is actually equals to P of Okay, maybe what we can do is usually when we say epsilon, right? So we always take this small positive number. Okay, we always consider epsilon is a very small positive number, like 0.00001. Okay, something like that. Okay, this is a 0.001. Something like that. Okay, so for this case, xn greater than epsilon. So this is actually xn greater than epsilon plus p of xn less than minus epsilon. Okay, so that means we exclude this. We can only look at this part. Okay, so therefore this will become, this thing will be equals to 1 over 2nr plus 1 over 2 power of n power of r. So this is how we can get this value. Okay, 1 over n. Okay, so this is 1 over n power of r. If we take the summations n from 1 to infinity, that will be this. And so this is less than infinity. Okay, so this is less than infinity when r is greater than 1. Okay, again, this is from calculus. When r is greater than 1, so this is always a finite number of the series. So now this is less than 0, less than infinity. Then we can see that this one must be equals to 0. Okay, by using the Borel-Cantelli lemma. Okay, so when this one equals 0, then we can look at here. Actually, sorry, we do not need the Borel-Cantelli lemma. We can actually directly apply this. Okay, when this one less than infinity, then we can see this is always almost surely. So actually, we do not need to apply this Borel-Cantelli lemma. We just need to apply these conditions. Will do. Yeah. Okay, this is not an example for it. Okay, so maybe we look at a better example. Let me see. This is 1920 question 4. Okay, so this is SQB7004 1920 SEM 1 question 4C. So you can get this. You can get this exam questions from the library. Okay, so this is question 4, part C. So this might be a better example. Huh? Okay, so yeah, I think great. We have time to look at it. So this is the questions. First of all, xi is a sequence of independence and identically distributed. So then this is a IID, okay, and also standard normal, random variable. So find the limiting distributions for this. What theorem is it? Forget it. I can't get the theorem number. Okay, so first of all, this question, we can use the central limit theorems to solve the problem. Okay. What is the theorems? Okay, forget it. Okay, doesn't matter. So this one, we can use the central limits to do it. First of all, xi independent. Okay, so for this one, so xi are IID. So standard normal random variable. So that means we're going to have E of xi will be 0, right? And also we have sigma square will be equals to 1. Okay, this is the case. IID, this, then we can apply the central limit theorems to do it. Okay. So by central limit theorems, okay, so we can have x1 plus x2 plus xn over sigma over square of n. So we'll converge. Okay, so okay, maybe I will just write this. I think doesn't matter. So sigma n. So this is actually equals to Sn over sigma. Okay, never mind. So I think we put it properly. Okay, we look at a solution for A. Okay. So given xi are independence and with identical distributions, and the mean is equal to 0, and variance is equals to 1, okay, because of standard normal distributions. So again, we can write Sn to be summating of xn, x1 plus up to Sn. So then, by central limit theorems, so Sn over sigma over square of n, so that is x1 plus x2 up to xn over. So because of sigma is equal to 1, so this is square of n. So exactly, this is the thing that we want to find, right? Okay, this part. This one will converge to standard, maybe I'll put Z. So this is a standard normal distributions. Okay, so this is part 1. Okay, now we look at part 2. So again, we have IID distributions, but now instead of standard normal, we have a chi-square. And the degree of freedom is equals to R. So I want to show that this one converge in property to R. Right? Okay, so we look at part 2. So in part 2, all the yi chi-square distribution. So in this case, that we can see the mean for the mean for chi-square distribution will be R. So you can follow the what do you call it, the Actually, we do not need the variant. So the variant is 2R. So for chi-square distributions, so the mean is 2R. So we only need this. Okay. So and also because of this is IID, right? Okay, then we can use our law of large number. So this is in distribution. We can use a weak law of large number. Okay, one reason with this, since we have used Sn over here, and then maybe we use another symbol for the summations. So we can just write Tn to be summating yi. Okay, we use this. So because we have used Sn to be summating xi. So I think that in this case, then we better don't repeat the symbol. Okay, Sn has been applied for xi, so then we take Tn instead of Sn. Okay, however, we can use the same formula, right? So we write Tn to be this. Yeah. Then by the weak law of large number, so we can have Pn over n will converge in probability to the main for it. Okay. So then we can get it. So we just need to verify it. So xi is this, as well as they are independent. Then we can have this one converge to r in converge to r in probability. Okay, and part 3, we want to look at it. Xn over this. Okay, to do this, we need to do several steps. All right.
Can I copy the question down real quick? Sorry, we just
once again. Okay, the question.
Yeah, just 1 second. I just take screenshot. Okay, thanks.
Okay,
thanks.
Okay, maybe yeah, this is a question. So let's have a look, sir. Okay, lastly, we want to look at this. Yeah, we want to look at these things. Okay, to do this, we do it one by one. Part C. Part 3. I'm also confused already. So what I want to prove. Okay, so we have this. How should I say this? Okay, maybe before we do number 3, so let's look at this thing first. Before the solution, let's do some observation first. Okay, first thing, we know this Sn over n. Okay, I think I don't want to use Sn. I think I better use x1 xn over what? Okay, over square of n. So this one converge in z in. A normal distribution. Okay, so this one. So if you okay, so if you are a bit confusing, this symbol is too complicated. What you can do is you can just simply let this one to be un v or vn. Okay, so that you just represent this with one random variable vn. So this is what we have done in part 1, and part 2 we have another one. So y1 plus y2 until yn over n. So this one will converge. Okay, again, still remember the relationship among this 5 convergence. So maybe I put it over here. Okay. So QM always imply L1, L1 implies P, P implies D, right? So P always implies D. So this one P, so that's why now I can just say this is D. Okay, directly say this D. So converge to R. Okay, take note. So this one R is a constant. Okay, so again, I think it might be a little bit confusing. This expression might be a little bit too complicated. So maybe you can write this one as a relatively simple. So let's say W N. And take note, so this one is a constant. Okay, so this one is a constant. I think maybe I put a box here. So this is not the solution yet. Just discussions. Okay. Okay, this one converge to Z in distribution. This one converge to D in distribution. R is a constant. Okay, now you refer back to theorems. So this is what we so-called the Slutsky theorems. Where's my theorems? Where's my theorems? Okay, forget about theorem. So maybe I can't remember the theorems, the location for theorem. So I just
5.3.2.
5.3. Thanks a lot. 5.3.2. Where is 5.3? Oh, okay. Okay, yeah, thanks. 5.3.2. So I think maybe down here. I hate the theorem because I'm also using X and Y. Okay, so you guys might need to switch your symbol. So what you can do is you can change this to V and sorry, this one to be W, this one to be Vn, all right? So if Wn converge to W, Vn converge to C, okay? So then this is your Wn, V, N converge to this. Okay, so that means okay, forget about this. You guys go and switch the symbol on your own, right? So what I'm trying to tell you is will be actually just a part B. Okay, so if the first one converge to X in distributions, and the second one converge to C. C is a constant. Okay, so the main thing is constant. Okay, must be a constant. All right. So the first one might not be constant, doesn't matter, but the second one has to be constant. So the first one converge to X in distribution. The second one, second random variable sequence converge to a constant C in distribution. Then the product of them. I'm using, okay, this one. Okay, so this one divided by this will converge to this in distributions. Okay, so now you're taking this to be X, this to be Y. Okay, you are applying these Slutsky theorems over here. So then you can see, so your Vn over Wn, that is, you can write this, so that will be okay, so it will directly become this. You guys go and work out the calculations. So we'll converge to Z over R in distribution. So this is my theorem 5.3.2 Part C. Okay, so this one converge to this in distribution. Okay, you have to check this property. This thing is in distribution. Yeah, so this one converge to Z in distribution. Wn converge to R in distribution. And most importantly, this is a constant. Yeah, if this is not constant, we cannot apply the theorems. Okay. So then by applying, these theorems, xn over yn, that means our vn over wn will converge to z over r in distributions. Okay, so that is the idea to solve this solution, the question. Okay, if you look at it, so this is the thing that we want to solve. Okay, right? That's the way to solve the question. Actually, it's not difficult. What you need to do is you just need to do the observation and apply, check the situation and see whether you can apply this, explain the situation, and then you explain which theorem you are using here. So I hope you can get how to solve these questions. Okay. Okay, so now we can look at the answer. So your answer is you just need to write down this story nicely and clearly. Okay. Okay, so now we look at the solution for 3. Okay, you may do the same thing. So what you can do is you can write Vn to be x1 plus xn over n, and I think square of n, right? And Wn to be y1 plus yn over n. Okay, so then by 1 and you can maybe you can just explain by 1 and convergent in probability and convergent in probability is sufficient for convergent in distributions. Okay, so we have x, we can have Vn converge to Z in distributions. So by 1, it converges in probability, and we know that convergent in probability is sufficient for convergent in distribution. So we have this. And also, in 2, Wn converge in R distributions, and R is a constant. So you can see that by Slutsky. What theorems? Theorem. Okay, I would just say, maybe I would just say Slutsky theorems. Okay, so by Slutsky theorems. Okay, and this is very important. First of all, you have to make sure this is a constant. If this is not a constant, we cannot apply the theorem. The theorem might not be true anymore. Okay, so by applying these Slutsky theorems, so we can see.
Dr. Lu, before that, a question is, for the statement by 1 and convergence in probability, why is that statement necessary for this solution? Because in 1, we already show that it's convergent in distribution, right?
No, we are actually...
Oh, no.
I think, sorry. Yes. Yeah, thank you. So actually, I think should be in, this is in P, right? Yeah, thank you. I think maybe we do not need this. We do not need this in part 1. Yeah, thank you. This explanation should be in part 2. Yeah, thanks. Here this is in probability, right? Yeah. This is in probability. I think maybe I should say this one in probability, and thank you for pointing out this. Convergence in probability is sufficient for convergence in distributions. Okay, so we know this Wn converge in R in distributions. Okay, so because of R is a constant, applying Slutsky theorem give Vn over Wn, that is, I think maybe you need to write one more step, so that is square of n xn plus yn over xn, y1 plus yn will converge in distribution z over r. Oh, I can't remember this. You guys go and check it out. I think this is please check this for me. So this one should be normal distribution mean with variance 1 over r square, or it's either 1 over r square or r square. So you guys go and check this out for me. Okay, this one or this, I don't know which one is it. Okay, so either, but I believe should be this. Should be this one. Yeah. But then please verify for me whether this or this. Okay, so I think that's it. All right, so right, there's the questions. Oh, okay. Someone. Okay, so that's it for the solutions. So actually, like I say, it's not that difficult, but you need to integrate several theorems to come up with a conclusion. Okay, so one by one. First of all, in part one, so you shall be using the central limit theorem for part 1. Okay, so it's quite straightforward. Using central limit theorem, we can get part 1. Actually, we do not need, because this is a standard normal distribution, so we can easily find the limit distribution for it. For part 2, we can use the law of large number. This is the law of large number. You can get it. Okay, so actually, part 3 is not difficult. We are using this as well as Slutsky theorems, and also we applying this P convergence in P implying the convergence in distribution. Okay, so like I said, not difficult. As you can see, the solution not very difficult. No serious calculation involved. However, you need to integrate several results to come up with the final answer. Okay, so maybe this is the one, very useful one, the Starsky theorems. Oh, okay. So actually, I plan to give another example, but now time's up already. I think maybe I should stop here now. Any questions before we end our lectures? No question, right? Yeah, I have an announcement. I'm not sure whether, okay, you are here or not. So, okay, where is my list? Okay, I suppose all of you attend this, right? Are you here? Yeah, one, Colin. Colin Lee, are you here? And second, Ching. Chong Kwan. Hasno Law. So three of you, are you here? Are you here? Please let me know whether you are here or not. Oh, Hasno, you are here. Okay. Colin? Chin, are you here? No. Okay, so for others, if you know Colin and Chin, please pass a message to them. Okay, Hasno, you are here, right? Okay, so I believe there's something wrong with the spectrum. Something wrong in spectrum. So I didn't receive your assignment. So please send me your assignment too. Okay. I don't believe you didn't upload it, but I believe you should have done it. But it happens before, some problem with the spectrum. So students uploaded. However, I didn't receive it. Okay. So for three of you, Colin, Chin, and Hasnot. So Hasnot, you're here, right? Okay. So after this, please send me your assignment too, because you cannot upload to the spectrum anymore. So you can either email me or you can do it in the Telegram, right?
Okay, doctor. Thank you.
Okay. So I trust you. I believe you won't forget it. So something went wrong in the spectrum. It happens before. So please email it or Telegram to me. Okay. Colin, are you here? Chin, are you here? No response. I believe yeah. Okay. Anyway, I have sent a message to them already. So and it happens. Any one of you know Colin and Chin, right? Please pass a message to them, right? Do me a favor. Okay. Thank you. Okay. I think that's it for today. Okay. Okay. So next week we will go to the last chapter, chapter 6. Okay. And then the week 14 will be the test and the last tutorial. Okay. Okay. So see you.